Today is the 7th of March. And here's the attendance form again for those of you on the Zoom. We'll do 1 or 2 graphical problems and then we'll kind of talk about other things. So let's graph the following. Let's graph f of x equal to x e to the negative x. And again, when we say the word graph, we mean all the things. We mean intercepts, asymptotes, relative extrema, inflection points, the whole shebang. So to graph this, we're going to start off with, yeah, sure. We're going to start off with the usual stuff. So let's, this question has something interesting in it. So we'll get there in a minute. But let's say we want to find first the intercepts. So the y-intercept, you're going to set x equal to 0. You're going to get f of 0 equal to 0 times, it doesn't really matter times whatever it is, but it is times e to the 0, but we get 0. Similarly, if we set y equal to 0 or the whole function equal to 0, we're going to get either x equal to 0, which is just x equal to 0, or the other factor equal to 0. But e to the anything will never equal 0 because e to the anything is always positive. Just think about the graph of e to the x or e to the negative x. So no solutions there. So our only intercept is the origin. How not exciting. Okay. How actually not helpful, because when graphing, it'd be really nice if we had more intercepts, but we don't. Let's go ahead and talk about the asymptotes. So vertical asymptotes. Do I have any division by 0? It's actually something you might not discount immediately. Oh, can you guys see all right? Sorry, I didn't like. How about that? Okay. If you want me to dim lights, let me know. But for now, I feel like that looks okay-ish. Let me do that though. So I would note here that technically you could write your function as x over e to the x. And there might be a concern about dividing by 0. But there isn't, because again, just like I said before, e to the x is always positive, so this denominator will never be 0. So no vertical asymptotes. The horizontal asymptotes, on the other hand, are where things get interesting. So there is going to be a horizontal asymptote here. Let's talk about where it's going to be. So to see where you might have horizontal asymptotes, we take the limits as you go way to the right or way to the left. Let's do the left-hand side first. So I take the limit as x goes to negative infinity of x times e to the negative x. What am I going to get? Well, I'm just going to plug it in and see what happens. If I plug it in, I'm going to get negative infinity times e to the negative infinity. And now you really have to ask yourself, are things big or small? Is e to the infinity big or small? Big. Negative infinity is also big. It's just negatively big. So when I say small, what do I mean? What number is small in my mind? What's the smallest number? If you're James. 0 is small because its magnitude is small. It doesn't have a very big value. Negative infinity is big. It's just really, really negatively big. So negative 1 billion, even though it's very negative, it's a large number. It's just negatively large. So you have a very large negative number times a very large positive number, and the overall result is very large negative number. So we don't have a horizontal asymptote to the left. As we go to the left, the function is going to go down, 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 down. On the other side of this, as x goes to infinity, this is where we're going to run into a problem. We have x times e to the negative x, which we could write as infinity times e to the negative infinity. But that's not super helpful because e to the negative infinity, if you think about the graph of e to the x, as you go to the left, that gets closer and closer and closer to 0. So what you really have is a really big number times a really small number. I don't want to say I really have times 0 because I don't. I have multiplication by a number that's getting closer and closer and closer to 0. But the number over here is getting really, really big. So what's the deal? This is actually where you would need to use L'Hopital's rule. So what you would really do here is you would rewrite this as the limit as x goes to infinity of x divided by e to the positive x. And then you see that you do have what's called an infinity over infinity indeterminate type. And infinity divided by infinity could be anything. In this particular case, the denominator is growing much, much, much faster than the numerator. Think about the graph of e to the x versus the graph of just y equals x. This is a much bigger thing. So in this case, we can just eyeball it today and say the numerator is a much smaller infinity than the denominator. And so this is going to be getting closer and closer and closer to 0. Later on, bless it, we'll talk about how we would actually do this. But for now, it's perfectly fine to say, yeah, an exponential thing is always going to outpace a linear or polynomial thing. So this is going to be 0. It'd be 0 even if that was x to the 100th power, because that polynomial would eventually get outpaced by an exponential. All right, that's all our before the first derivative stuff. So let's find the first derivative. The first derivative here is going to be product rule. 1 times e to the negative x plus x times the derivative of e to the negative x is e to the negative x times the derivative of negative x. Normally, we would just take the derivative and leave it like that, but here we're actually trying to do something with it. We want to find the critical points. So we're going to set that derivative equal to 0 and solve. And I would suggest whenever you're trying to find the critical points, you really want to leave everything on the left side of 0, or whichever side of 0 you've written it on, and just factor as much as possible. You really, really, really don't want to like bring this over to the other side and try to like manipulate both sides of this equation. You just want to manipulate the left side. So here, I'm going to factor out an e to the negative x. I'm left with a 1 plus x times negative 1 or a 1 minus x. And you can either leave it like that, or if you prefer, you could write it as 1 minus x over e to the x equal to 0. Technically, I should have said 0 or undefined, but we can look at this and see that it's never undefined. Because again, dividing by e to the x, that denominator will never be 0. So there's never any x value that makes it undefined. Here, the x value that does make this equal to 0 is just x equal to 1. That's my critical value. So then put that number on the number line. Pick a number larger than 1, like 7. 1 minus 7 is negative. E to the negative 7 is positive or negative? E to the something is always right. So it's a positive times a negative, which is going to be negative. And then you can either keep doing the same thing, or you could say the 1 came from this factor. This factor has an odd power of 1, which means the sign is going to change. Or you can plug in 0 and say e to the 0 is 1, 1 minus 0 is 1, and a 1 times a 1 is a positive number, which is 1. So our function's increasing, then decreasing. So we have a relative what? Maximum or minimum? The relative maximum at the point 1 comma f of 1, which I should actually find the value. If I plug in 1 to the original function, f of 1 is equal to 1 times e to the negative 1, which is 1 over e. Which, just for your knowledge, is approximately 0.3. That's what because 1 over e comes up often enough that it's good to have an idea of what it is. We know that e is about 2.7, so 1 over e is not too far from 1/3, but it's closer to 0.3. It's like 0.31 something, I think. So let's find the second derivative stuff. We can probably fit it on this page. Let's not. We don't need to squeeze it in there though. We got all the paper in the world. So second derivative stuff. So looking back at my first derivative, now I will say it's probably to my benefit to actually simplify my first derivative. Actually, so I'm gonna back that up. Normally, I would say that I would not use the factored version of my first derivative to take the second derivative, but in this case, I think I am going to. Really, it's up to you. You can look at this or this and decide which thing you want to take the derivative of. That's also though why I do recommend, one of the reasons why I recommend leaving everything on the same side. So the thing that you're left with on the left-hand side is still your first derivative, just factored. Is there a question, Jeannie? To find the inflection points and the concavity. Because the problem told me to. So when I read a problem that says graph something, I am assuming that they mean find intercepts, asymptotes, relative extrema, inflection points. And so to find the inflection points, I have to find the second derivative. The terrible noise outside. The other thing I want to say about this is the reason why you want to do this in this factor way over here, which I forgot to mention here, is factoring it like this and leaving everything on the same side makes it much easier to determine whether you have a negative value overall or a positive value overall. Whereas if you don't factor it, you try and leave it like this, it's much, much harder. So definitely writing the left-hand side or your derivative in its fully factored form is advantageous. And I highly recommend trying to do it that way. My second derivative, yeah, let's go ahead and say we have the first derivative is just e to the negative x times 1 minus x. I suppose if you wanted to use the quotient rule, you could write it as 1 minus x over e to the x. I don't want to use the quotient rule. Second derivative is going to be the derivative of e to the negative x, which is negative e to the negative x times the other thing left alone, plus leave e to the negative x alone, multiply by the derivative of 1 minus x, which is negative 1. I'm again going to factor out what I can. So I'm going to factor out an e to the negative x. I'm left with, maybe I should factor out the negative e to the negative x. Sure, why not? Let's factor out a negative e to the negative x. So here I'm left with a 1 minus x. Here I'm left with a plus 1. And so then I'm going to end up with negative e to the negative x times 2 minus x. And if I set that equal to 0, the only critical value I'm going to get is x equal to positive 2. Again, this e to the negative x doesn't give me any other critical value because that'll never equal 0. Then we do the same sort of thing. We draw our number line for our second derivative. We plot the only critical point we have on there, and we test to see what's happening. So you pick a number larger than 2, like 3. 2 minus 3 is negative. E to the anything is positive, and then the negative there makes it a negative times a positive times a negative, which is positive overall. And if I plug in, you can actually plug in 0 and get the value, or you can just say e to the 0 is positive, negative e to the 0 is negative, and then 2 minus 0 is positive, so a negative times a positive is negative. Or you could say 2 came from that factor has an odd power, so sign changes. So we're concave up over here, concave down over here. We definitely have an inflection point at 2 comma f of 2. And f of 2, if you plug 2 back into the original function, which was x e to the negative x, f of 2 is going to be 2 times e to the negative 2, or 2 over e squared. In my mind, e squared is about 8. Like it's a little bit less than 8, I think. I don't actually know. Let's find out. What is e squared approximately equal to? I mean, it's close to 8. I don't remember if it's bigger or smaller. Let's see. Where are we at? E squared is 7.38 approximately. So e squared, close-ish to 8. So 2 over e squared is about 2 over 8, which is about 1/4, or 0.25. Again, not super important that you know that, but it's just going to help us graph it a little bit better. All right, I think we found all the things we can find. Let's see if we can draw this graph. So let's see. Looking back at all my stuff, I have an intercept at the origin. And then I have a relative maximum at x equal to 1. I have an inflection point at x equal to 2. And on my y-axis, I would like to make my y-scale maybe a little bit larger. Like graphing the point 1 comma 0.3 would be the drawing the maximum right there seems like it's going to be difficult to make it look nice. So I'm going to scale up my y-axis a little bit, which is totally fine. Maybe draw it like right there. Maybe inflection point's going to be like right there. So then looking at my first derivative sign chart to help me get the shape of the graph, I can see that my function is going to be increasing until I get to 1 and then decreasing afterwards. You could have probably figured out that you had to have a horizontal asymptote over here because right of 1, the function has to be decreasing, but I don't have any more x-intercepts. So I just have to get smaller and smaller and smaller and getting closer and closer to 0. There's not really any other behavior I could have. But it's good to be able to find the horizontal asymptotes without just relying on graphical methods. And if you wanted to, you could label this point as 1, 1 over e. This point is 2, 2 over e squared. And that's about as good as it gets. Questions about this graph? Yeah. So one more time? Oh, yeah, it's definitely, yes. Maybe. That look a little easier to see. Cool. So there's our path. Okay, so that's pretty much the process for graphing things. Oh, we should do one more. I got one other graph in mind. We'll do one more and then we will move on to greener pastures. See if I can find the one I'm thinking of here. 1 second. Not that one. That one's gross. Yeah, that one's kind of terrible. We should do it. Okay, one more and then we'll move on. So let's say our function is f of x equal to x cubed over x squared minus 1. Yeah, we'll do that. Okay, so let's find the things. And I'm just going to do the usual stuff from the intercepts all the way through the second derivative. And I'm always going to start with the intercepts. So y-intercept, f of 0 is definitely 0 over -1, which is 0. Often the origin is going to be 1-year points. Not always, but a lot of the time. X-intercepts. For a rational function, you can skip to just setting the numerator equal to 0. So we're going to set x cubed equal to 0, and we're just going to get x equal to 0. So that one more time. I'm not plugging anything in. So what I'm really doing, what I'm skipping is I'm actually setting the entire function equal to 0. But then the first step is to multiply both sides by the denominator. So I multiply the left side by the denominator, I get x cubed. I multiply the right side by the denominator, I get 0 times x squared minus 1, which is just 0. So that's how I'm getting from there to there. I'm just taking this and I'm saying, oh, what if I multiplied both sides by x squared minus 1? On the left-hand side, those are both 0, or those cancel. On the right-hand side, 0 times anything is just 0. So that's how I'm getting this. Oh. Okay, asymptotes. Vertical asymptote. Set the denominator equal to 0. I should briefly mention, all of this is under the guise or the assumption that in your original expression, you have done any factoring and canceling that might have been possible. So like if there was an x plus 3 times over an x plus 3 that would have canceled out, we've already dealt with that. So after you factored and canceled any possible factors, then you set the denominator equal to 0. So here, I'm going to get 2 vertical asymptotes because this factors as x minus 1 times x plus 1 equal to 0. So we're going to get x equal to positive 1 and x equal to -1. Okay. How about a horizontal asymptote? Do I have one? I know it's been a while since we talked about so if I take the limit as x goes to infinity of x cubed over x squared minus 1, what's growing bigger faster, the numerator or the denominator? The numerator. The numerator is growing bigger faster. That means this thing's just getting larger and larger and larger. meaning it doesn't have a limit that's a finite value. This limit is going to be positive infinity to the left, to the right, and negative infinity to the left. If you wanted to, you could do the work of dividing the top and bottom by the largest power of x in the denominator. If I divide the top and bottom by x squared, I'm going to get x cubed over x squared on top over x squared minus 1 over x squared, which becomes the limit as x goes to negative infinity of x over 1 minus 1 over x. The 1 over x goes to 0, and the x goes to negative infinity. So we get negative infinity, which means we don't have a horizontal asymptote. Now, here's something I don't think we've talked about, but that is true. If you have a rational function and the degree on top is exactly 1 bigger than the degree on the bottom, which is the case here, we have a slant asymptote, also called an oblique. So how do we find the slant asymptote? Polynomial division. So we have a slant asymptote because the degree on top is equal to the degree on the bottom plus 1. That's always true. If the degree on, if it's a rational function, meaning it's a polynomial over a polynomial, and the degree on top is 1 larger than the degree on the bottom, then you do have a slant asymptote. It's not a terrible thing to have. We're just going to do the division here. So we're going to say x squared minus 1 dividing into x cubed. You're going to get x squared times x would give me x cubed. X times x squared is x cubed minus x. We subtract. X cubed minus x cubed is 0. The no x minus x would be plus x. And now since this x has a lesser degree than our divisor, that's our remainder. Now I don't love this example because the quotient and the remainder happen to be the same, which I feel like makes it confusing. But what this is telling us is that x cubed divided by x squared minus 1 is equal to the quotient x plus the remainder x. Let's use a different color here. Divided by the divisor, x squared minus 1. You don't really have to do all this normally, right? You could really just stop here once you get the total numerator. That's all you really need. So our slant asymptote is y equal to x, the straight line. And what's happening here is that as x gets really, really large, this remainder part here gets closer and closer and closer to 0 because the degree on top is smaller than the degree on the bottom. And so the dominating feature of this rational function is that it looks like x plus something that's very, very small as you move further away from the middle. We'll graph it and we'll kind of see better what it looks like, but that's really what's happening. Okay, we found all of the function stuff. Let's go find the first derivative stuff. Ooh, first derivative is going to be maybe kind of gnarly. It's all right. We know how to take the quotient of something. So the derivative here is going to be the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the denominator squared. I'm not loving this. Oh, well. We definitely need to simplify this before we can start trying to find the critical points. So multiplying off the top, x squared times 3x squared is 3x to the 4th, minus 1 times 3x squared is minus 3x squared, minus x cubed times 2x is 2x to the 4th, all over x squared minus 1 squared. 3x to the 4th minus 2x to the 4th is x to the 4th, minus 3x cubed over x squared minus 1 squared. Finally, I can factor out an x cubed from the top, and I'm left with an x minus 3 over x squared minus 1 squared. Somebody be brave and tell me one of the critical values. What x value is going to make this equal to 0? Or in the chat, people can type things in the chat too. 3, awesome. 3 is one of them. What's another one? 1 is, but no, 1 is because 1 makes it undefined. In fact, your vertical asymptotes are always going to count as what I like to call pseudo-critical points. So you should always be including your vertical asymptotes. But there's one more value. And I feel like for some reason it's the one that's easiest to find, but also really easy to miss for some reason. If you set x equal to 0, 0 cubed is 0 times 1 times 0 minus 3 is still 0. So since x to a power is a factor, x equal to 0 is a critical value. So 3 plus or minus 1 and 0. So I will point out that the 3 and the 0 are the real critical values because they're actually in the domain of the original function, whereas the plus or minus 1 are the fake or pseudo critical values. We still need to include them on our number line for the first derivative. Questions about any of this specifically? Yeah. Sure. So what I did, like from here to here, or maybe I might have made a mistake. That's a very you might have seen yeah, good call. I don't get it either. Thank you. So x squared times 3x squared is 3x to the fourth. Minus 1 times 3x squared is 3x squared. Good call. So let's fix this. So this should be then 3x to the fourth minus 2x to the fourth. It's still x to the fourth, but this should be a minus 3x squared, which means I can only factor out an x squared, not an x cubed. So I factor out an x squared, I'm left with not x minus 3, but x squared minus 3, which is so much less pleasant. So that means 3 is no longer our critical value. It's actually plus or minus the square root of 3. Because of x squared minus, so what I really could do, and I'm trying not to write all the things down because I don't think you need to write all the things down, but what you could do is you could set each factor equal to 0, like x squared equals 0, it gives you x equal to 0. X squared minus 3 equal to 0 gives you x equal to plus or minus root 3. And x squared minus 1 equal to 0 gives you x equal to plus or minus 1. That's how I'm getting all those critical values. Okay, so now we're going to put them on the number line, and we have to make sure we put them in the correct order. So what's my biggest critical value? 0, positive 1, or positive square root of 3? Definitely not 0. What's bigger, root 3 or 1? Yeah. I am always thinking of root 3 as, right, I mean, if I said what's bigger, root 3 or 2, the way I would actually figure that out, root 3 versus 2, is write 2 as a square root. Oh, yeah, the square root of 4 is definitely bigger than the square root of 3 because 4 is bigger than 3. That's what I'm doing over here as well. Root 3 is bigger than 1 because root 3 is bigger than the square root of 1 because 3 is bigger than 1. So on our number line, we've got 0, 1, root 3, and then negative 1, negative root 3. And this is a time where it's going to be worth our while to factor this completely. So check this out. I'm going to do a little bit more factoring here. On top, I've got x squared. X squared minus 3 does factor. It factors as x minus root 3 times x plus root 3. It's kind of gross. And x squared minus 1 squared also factors. But really, I don't need to factor it, and here's why. X squared minus 1 squared is always positive. So is x squared. So these parts are always positive. The only thing that's really going to affect what's going on is what's happening with x minus root 3 and x plus root 3. Pick a number bigger than root 3, like 5. Positive, 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 positive. Are we going to change signs when we go from this side of root 3 to that side of root 3? Well, the root 3 came from there. The power is odd. If the power is odd, do we change? Yes, we do. Do we change? The 1 came from here. This thing is squared. It's going to always be positive, so we don't change. We stay the same. The 0 came from there. We stay the same. The negative 1 came from there. We stay the same. The negative root 3 came from there. We change. So our function is increasing, decreasing, 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 increasing. And just to kind of remind you, the -1 and the 1 are where we have asymptotes. So this one's going to look like on the left side of -1 going down to negative infinity, on the right side of -1 going down coming from positive infinity. Right, so I'm not going to graph the whole thing just yet, but I know that like at -1, it's going to be going down and then down like that. Because it's decreasing on the left and decreasing on the right. That's how I'm seeing that. Okay, I guess we should talk about our relative. This problem is kind of gross. So our relative extrema at -√3, we have a relative maximum at x equal to -√3. And at positive √3, we have a relative minimum. All right, let's find, we really want to find the second derivative stuff? I guess we do. I feel like I'm pretty sure we end up getting nothing from the second derivative. Oh no, I think there's one inflection point. Okay, so let's look at this whole list here and see what's the thing that I want to take the second derivative of. I think it's going to be this. That's, to me, looking like the thing that's easiest to deal with. I don't want to use the product rule if I can help it. I don't really want to multiply at the bottom, though, because I know for quotient rule, the denominator written in the factor form is going to be convenient because it's going to kind of keep showing up. So I'll take the derivative of that. Goodness gracious. So f prime is x to the fourth minus 3x squared over x squared minus 1 squared. And then taking the derivative of that, let's use the quotient rule. F double prime is going to be the bottom, x squared minus 1 squared, times the derivative of the top, which is 4x cubed minus 6x, minus the top, x to the fourth minus 3x squared, times the derivative of the bottom, which is going to require the chain rule. It's going to be 2 times x squared minus 1 to the first, times the derivative of that, which is 2x, over x squared minus 1 squared squared. Now we need to simplify. Now here's the thing. If your denominator was already something raised to a power, and then you've taken the derivative of that again, that factor, x squared minus 1, should be able to be factored out from the numerator. And I definitely see an x squared minus 1 squared and an x squared minus 1 to the first. So I can factor that and x squared minus 1 to the first out of the numerator. So I'm going to rewrite this as f double prime of x equal to x squared minus 1 times, in this first piece, I'm left with still an x squared minus 1 times a 4x cubed minus 6x, minus, in the second piece, I have an x to the fourth minus 3x squared times a 2 times another 2 times no x squared minus 1 because that part got factored out, then times another 2x. I'm going to make that 2, yeah, let's make it all divided by x squared minus 1 to the fourth. We cancel an x squared minus 1 with an x squared minus 1. And then we try our best to simplify this monstrosity in here. So we're going to get x squared times 4x cubed is 4x to the fifth. X squared times minus 6x is minus 6x cubed. Minus 1 times that is minus 4x cubed. Minus 1 times minus 6x is plus 6x. Minus, this is a 4x right here. 4x times x to the fourth is 4x to the fifth. 4x times negative 3x squared is minus 12x cubed. Yeah. All over x squared minus 1 cubed. And then finally, we can simplify this and get the 4x to the fifth. We're going to cancel. Let's write it out. So minus 6x cubed minus 4x cubed is minus 10x cubed plus 6x minus 4x to the fifth plus 12x cubed. X squared minus 1 cubed is equal to those cancel. We're left with a 12 minus 10, so a 2x cubed plus 6x over x squared minus 1 cubed. Factoring out a 2x from the top, we're left with an x squared plus 3. Whew. So our critical points here are x equal to 0 and plus or minus 1. This factor here, this x squared plus 3, doesn't give us anything because x squared plus 3 equal to 0 would mean x would have to be the square root of a negative number. So I know that was kind of a lot. Any questions or clarifications before we do the number line for this thing? Okay. You're always welcome to ask no matter where we are. Here's my number line for the second derivative. Picking a number larger than 1, like 2, positive, positive, positive. Picking a number between 0 and 1, like 1/2, positive, positive, negative, and the negative number cubed is still negative. So it's going to be negative overall. Then we're going to change signs to 0 as well because 0 came from x to the first, and that has an odd power. But you can pick negative 1/2 and say negative, positive. Negative 1/2 squared is 1/4 minus 1. It's still negative. So yeah, negative, negative is positive. And finally, over on the other side here, we're going to have negative 3. So negative, negative, positive. So our function is concave down, concave up, concave down, concave up. All right, I'm going to try and trick you right now. Show me on your fingers, how many inflection points do I have? Don't get tricked. This many is too many. No, not that finger. This many. This is the right number. Why not this many? Because we have a vertical asymptote at -1 and a +1. Which, if you start graphing it, you'll see, oh yeah, I couldn't have had an inflection point there. But it's good to always remember that you have asymptotes. So we have one inflection point. It's at x equal to 0, y equal to 0. And yes, I know I didn't find the y values for my relative maximum and relative minimum, so I really didn't want to. Not because you shouldn't, just because I was like, there's so much to do with this problem. Let's just forget about that part. Okay, let's graph this beast, which has taken 3 pages of work so far. That's just because I'm a big writer, though. Not really. I would like to. I would like to pretend I'm a big writer, but I think you all know that my writing is not usually big enough to really be easily seen. So number line, I got my 0, 0 point. I have vertical asymptotes at +1 and then -1. I have a slant asymptote at y equals x, which is going to look like just the line y equals x, but you want to draw it dashed. Okay. And then what else? Nothing else from this page. We have a relative maximum at -√3. So -√3 is over here left of -1, like right here maybe. And I have a relative maximum. So it's going to be like right here. So it probably would have been good to find the y value. I will tell you the y value is some negative number. And it's going to do something like this. Right? It's a relative maximum. The function's increasing from the left, decreasing after that. Similarly, over at +√3, I have a relative minimum. So the function is going to do something like this. Bottoming out right there. And then the only other thing I have is an inflection point at the origin. So I think I'm ready to draw this thing. So here's what's going to happen. Where's my first derivative stuff? So my first derivative sign chart, I'm going to be increasing until I get to this relative maximum, decreasing afterwards, so I get to that vertical asymptote, and then to the right of -1, still decreasing, concave up right now, and then when I get to the 0, 0, I'm going to switch my concavity and become concave down, but still decreasing. To the right of 1, still decreasing. And after √3, increasing and getting closer and closer and closer to my slant asymptote. So if you were to graph this function and zoom way out, it would look kind of like just like y equals x. In fact, we can do that. There's one other thing I maybe should have said about this function, but let's graph this here real quickly. So let me just show you this so you can see it. We have y equal to x cubed. I know you can't see it yet. Divided by x squared minus 1. So come on, get over there. So there's the function. All right. I'm always like looking way over there. I could be looking at the screen right in front of me. Real brilliant. So, and also here's my slant asymptote. Y equals x. And just like a horizontal asymptote, what's happening is that as you move further from the middle, the function gets closer and closer to that asymptotic line. And if you start zooming out, you can see, oh yeah, the middle, what's happening in the middle is kind of wild, but then after that, you're just getting closer and closer to the line, y equals x. It looks pretty much like y equals x, even though when you zoom in, there is always going to be some small amount of separation between those two functions. They just look like, right? Like they look like they're on top of each other, but if you zoomed in close enough, you can see that there's separation. So you're just getting closer and closer to that, but not actually equal to that. Neat. All right, I think that's enough terrible graphing for today. Let's talk about optimization for a bit. I feel like there's something else I'm keep thinking about with this function here, but I'm not remembering what it is. All right. Oh, I will point out that our concavity works, right? It's concave down over here, concave up here, concave down here, concave up here. So definitely the concavity. Usually you don't have to try super hard to make the concavity work. It's kind of just like if you graph all the things you have and you adhere to the first derivative sign chart, increasing, decreasing, the concavity kind of just gets drawn the way it should. Unless you have something that is weirdly not differentiable somewhere, then you might have some weird concavity stuff. All right. Yeah, that was gross. Let's talk about optimization. Okay. Give me one second. My wife keeps texting me and I feel like it might be important. So no, it's not that. Okay, fine. Totally fine. Just, sometimes you're like, why are you texting so much? Okay. Well, let's look at this first question. I think this question was written in Halloween, around Halloween. We're going to build a trick or treat box or just a box. And here's what we have. We have 108 square inches of material, maybe cardboard, to make an open top box. An open top box with a square base. And the question is, what dimensions of the box will give the maximum possible volume? So the way I kind of conceptualize these problems is there's almost always something you want to optimize, either maximize or minimize, and then there's some constraint, some limiting piece of information. So here, and I should say, before we do any of that, though, what we really start off is by drawing a picture. So I'm going to draw a picture of a box that has a square base. Really loving whatever's happening outside there. There's my box with a square base. And I'm going to call this side X. And I'm going to call this side also X because if the base is square, those two sides should always have the same length. And then let's call this side Y. I will point out there's lots of different boxes we could construct that would meet our constraint. We could draw or have a box that's like, say, 2 inches by 2 inches by 13 inches. right? That box has the right amount of surface area. This front face here is 26 square inches. There's 4 of them, which is equal to 104. And then the base also has 4 square inches, which is 108. So there's one potential box that would meet the criteria. But that box probably doesn't have the most volume. The volume of that box is 2 times 2 times 13, which is like 52 cubic inches. It's probably a more volumetric box, or voluminous. There's a more voluminous box. So here's the deal. We want to set up 2 equations. First, the thing we want to maximize. So we want to maximize volume. So the way I've drawn this box, what's the volume? Or what's the equation for the volume? Well, the volume is going to equal length times depth times height. X times y. I always like asking this question. How many variables are there in my volume equation? Too many. 2 is too many. More than 1 is too many. At least in 21A. In 21C, 2 is fine. We can optimize functions of 2 variables in 21C. But in 21A, 2 variables is too many because we only know how to maximize or minimize functions of 1 variable. So we need some other way of getting an equation relating x and y. We need a constraint. And in this case, the constraint is that we have 108 square inches of material to use. Now, we want to translate that constraint into an equation. When they talk about how much material you have to use, what they're really talking about is how much surface area you can have in your shape or your construction. So in this case, the surface area of this box should be no greater than 108. Now, it wouldn't make sense to use less because you could have made it bigger by using more. So we're going to set the surface area equal to 108 square inches. So we're going to set the surface area equal to 108 square inches. But we should actually write the equation for the surface area. So let me kind of draw the behind the scenes part of this box here. This box, I should say, this open topped box has 5 sides. They're all either rectangles or, well, I mean, they're all rectangles. One of them's a square, which is a rectangle. So our surface area equation, the bottom side has an area of x times x. The front side has an area of x times y. And so do the other 3 sides. The right side here is x times y. The back side here is x times y. The left side here is x times y. So I really have 4 of those x times y sides. I'm going to set that equal to 108. Something that I've noticed over the years, which I think is worthwhile, is that your constraint thing should always be equal to a number. Whereas the thing you're trying to maximize is just an equation that's not equal to some number. Because if you knew what number it was equal to, you wouldn't be trying to make it as big as possible. It would already be equal to a number. So the thing you're trying to optimize should never be equal to a number until you've actually done the work. All right, so then after we find our thing we want to maximize and our constraint, we typically take this constraint equation and isolate one of the variables and sub it back into the thing you want to maximize equation. In this equation, there is an obvious better choice as to which thing I should try to get by itself. And the better choice here is y. I have an x squared and an x. Solving for x here would probably require the use of the quadratic formula, which is terrible. I should definitely solve for y. So isolate a variable in your constraint equation. So I'm going to say that 4xy equals 108 minus x squared, and then divide both sides by 4x to get y equal to 108 minus x squared divided by 4x. And it might be worthwhile to simplify this, but I'm going to wait until I plug it back in to see if simplifying is really kind of necessary. So now we're going to take that, we're going to plug that into the thing we want to maximize. So we're going to then plug y equal to 108 minus x squared over 4x in for y in the equation, volume equals x squared times y. So now our new volume equation is going to be x squared times 108 minus x squared over 4x. And now our volume is a function of one variable. And we are capable of maximizing or minimizing functions of one variable. I would really not like to use the quotient rule here. And more importantly, I really don't have to use the quotient rule here because I can cancel an x there and say this is really equal to x to the first times 108 minus x squared over 4. Or if I distribute the x, 108x minus x cubed over 4. Or if I write this kind of in the best way possible, the volume as a function of x is 1/4 times 108x minus x cubed. And now it's going to be not terrible at all to take the derivative. Yeah, okay. So the derivative here is going to be 1/4 times 108 minus 3x squared. What's the... Well, what do I guess I just need to solve this now. So I would probably multiply both sides by 4. Say 108 minus 3x squared equals 0. Factor out of 3. Or don't factor. Oh, yeah. Kind of breaking my own rules here. Sorry, I'm trying to think about how I want to say this. Do that. No, so I know in the previous problems I was saying like you should kind of leave everything on the same side. That's less true in these optimization problems. It's definitely true when you're graphing because you want to kind of see how the thing looks as it is. But here, if we're just trying to solve this equation, it's really okay to move things around. So you could divide both sides by 3 and get 36 minus x squared equal to 0. Or you could have made the choice to say 108 equals 3x squared. And then 108 divided by 3 is equal to x squared. Either way, you're getting x equal to positive 6 or negative 6. And one of those answers doesn't make any sense. X being the length of this box, the length of the side of a box, definitely should not be negative. So x should not be negative 6. All right, here's an important question. We found this critical point. Does it actually maximize the volume of the box? I don't know. Maybe it gives us a minimum volume. That'd be terrible. I'd made the worst trick-or-treat box I could have. So typically with these optimization problems, there's often some level of being required to check to make sure that you actually got the thing that you wanted to get. Now, in reality, these problems get asked in such a way is that if you find the one critical value that is going to be there, it's going to give you the thing you want. However, there are some trickier questions where you actually get multiple critical values, and then you really do actually have to check to see which one gives you a maximum or minimum. This is actually an excellent time to introduce what's called the second derivative test, which you may have talked about in class. So not finding the critical points of the second derivative, but using the second derivative to tell you if your function has a maximum or a minimum, meaning if your first derivative is doing this or doing this. So here's the idea. Let's take the second derivative here. Second derivative is going to be not too terrible. It's going to be 1/4 times 100, the derivative of 108 is 0, derivative of 3x squared is 6x, which is just negative 6/4 or negative 3/2 times x. And now you're going to plug in your critical point. So plug in 6. We know that at 6, we might have a max or a min or an inflection point. So before I do this, let me point out, we might have something that looks like this at x equal to 6. Or we might have something that looks like this at x equal to 6. Or we might have something that looks like this. Because we know that at 6, the derivative is equal to 0, meaning the tangent line is horizontal. So we have something like one of those situations. But now check this out. If you plug in 6 to the second derivative, I'm going to get -3/2 times 6. And I don't really care that it's equal to -9. I just care that it's negative. So now, if the second derivative is negative, that means the function is concave which way? Actually down. So if the second derivative is negative, it's concave down. So if it's concave down, it's this picture here. And if it's concave down, that means our critical point is that a maximum or a minimum? It definitely has to be a maximum. There's no other choice. That's the nature of the second derivative test. You take your critical point from your first derivative, you plug it into your second derivative. If your second derivative is negative, that means you were concave down and you had to have a max. On the other hand, if your second derivative was positive, that means you're concave up and you had to have a minimum. And then if you're unlucky and your second derivative ends up equaling 0, then you have to use a different test. Because it could be anything in that situation. There's something else I want to say here. Oh, so not quite done. X equals 6 inches gives us a max. But we didn't quite finish the question because the question said to find the dimensions, plural, of the box that maximize. So then we have to go back and find the y value. Luckily, not luckily, every time this is going to be true, there is already an equation that tells us how to find y. Y is going to equal 108 minus 6 squared over 4 times 6. That's 108 minus 36, which is 72. 72 divided by 24 is equal to 3. 3? Yeah, 3. 3? That sounds right. My brain doesn't feel like it's right. Yeah, that's right. So those are the dimensions of the box with the most volume. X would equal 6 inches. X would equal 6 inches. Y would equal 3 inches. And although they didn't ask us for it, we could actually find the vol. Oh, no, I don't want to say that actually. So I will say this, even though I don't want to say it. Coincidentally, and it is very much a coincidence here, the volume of this box happens to also be 108 cubic inches. Because 6 times 6 times 3 is equal to 108. But that is purely coincidental. You should not read anything into that. It's not because the square it should not usually be the same as what the surface area is. Just it happens to be because of the nature of these particular numbers, we end up getting the same value. But that's why I didn't even want to say anything. Because like you shouldn't read anything into that. There's nothing to see behind the magic curtain. I just turn off the light. What happened? I don't know. Anyway, you guys can still see that, right? Yeah, okay. All right, so for these optimization problems, a lot of them kind of depend upon knowing equations for volumes and surface areas of shapes. Let's look at another example. I don't love this. Let's change that up. So, yeah, question 2. What are the dimensions of a cylindrical can that has a volume of, let's say, 100 cubic centimeters? I phrased this terribly. What are the dimensions of a cylindrical can that has a volume of 100 cubic centimeters that minimize the amount of materials used in its construction? Or put more concisely, what are the dimensions that minimize the amount of surface area required to construct a can that holds a volume of 100 cubic centimeters? A cylindrical can. Let's draw ourselves a can. That's a kind of short can. Although have you ever seen like those little mini Cokes that like are practically as tall as they are wide? That's what I'm imagining when I'm drawing this cylindrical can here. This can with a height of we don't know and a radius of we also don't know. Wow. Wow. Really struggling to draw that there. So I personally like to start off with the thing that I'm trying to optimize. So here I'm trying to minimize the surface area. I'm going to minimize the surface area. Ooh, the surface area of a cylinder. Well, I know two of the areas. I know that the top is a circle and the bottom is a circle. So the surface area, at least the bottom and the top, are going to be pi r squared plus another pi r squared, which is 2 pi r squared. That's going to be the bottom plus the top. Now, what about the sides? Here's what I think of when I think about the sides. I think about a roll of paper towels. You take one paper towel off that goes all the way around perfectly, and you unroll it, and what shape do you have? Rectangle. And we know how to find the area of a rectangle. So what we're going to do is we're going to take this paper towel here that goes around like that. And we're going to say, okay, unroll that. And you've got a rectangle whose height is still the height and whose length is the what of the circle. What do we call that? The circumference of the circle. And the circumference of the circle is equal to 2 times pi times the radius of the circle. So the area of this rectangle that goes all the way around the cylinder is 2 times pi times the radius times the height. And that's what we're going to add up here. And this is essentially the around part. All right, here's my favorite question. How many variables are in my equation of the thing I want to minimize? How many are there? Too many. Oh, come on. It's so fun to say. Too many. So then it's really just a reminder that you need another equation. You need an equation so that you can write this as a function of one variable. So we need our constraint. And we are constrained by the fact that we want this can to hold 100 cubic centimeters of Coca-Cola or whatever we're putting in it. So our constraint is that the volume has to equal 100. I probably should have made it 100 pi, but I didn't. So the volume here is going to be, well, the equation for the volume of a cylinder is the base area, which is the area of the circle, times the height. We want that to be 100. A lot of the times here you're going to be faced with a choice. Most of the time it should be relatively obvious which variable is better to isolate. If we had to choose here based on this equation and also what we're plugging into, should we isolate H or should we isolate R? Definitely H, 100%. For two reasons. One, I don't want to take a square root if I don't have to. And two, I'd have to plug R into both that spot and that spot. So it's just less work to solve for H to plug in there. So usually it should be, if it seems like one's a more obvious choice, pick that one. If things start looking terrible, you might try going the other way. And we'll say things are going to start looking terrible here because of the nature of these numbers. So here we're going to get H equal to 100 divided by pi R squared. And we're going to plug that in to our surface area. So now we're going to have our equation is going to be that the surface area is equal to 2 pi R squared plus 2 pi R times 100 over pi R squared. We should definitely simplify this before we start differentiating. So I would rewrite this as, I can rewrite it here, as 2 pi R squared. Pi's cancel here, and also an R cancels. So I have 2 times 100. Instead of writing 200 divided by R, let's write 200 times R to the negative first. So that the differentiation is not too terrible. Now we're going to find the critical values. So we're going to take the derivative. So S surface area prime is equal to 4 pi r minus 200 r to the negative second. And I will warn you, this is where the numbers are going to get a little bit gross. So here's how I would deal with this. I would rewrite this as 4 pi r equal to positive 200 divided by r squared. I would multiply both sides by r squared to get 4r cubed equal to, 4 pi r cubed. Ugh. I guess pi times 4 times r cubed. That's terrible, but it's the same thing. Equal to 200. And finally, well, not finally, r cubed equal to 200 divided by 4 pi. 200 over 4 is 50. So r is equal to the cube root of 50 divided by pi. Which I will fully admit is disgusting. All right. Important question here. Does this minimize the surface area? Well, there's a couple ways to do this. We could do the same thing we did before. We could say we're going to use a second derivative test and see if it's, in this case, we would want to be able to plug this into the second derivative and get a positive second derivative so that it's concave down, concave up, which would mean we'd have a minimum. You could also use the first derivative test, though. There is a first derivative test that says if you have one critical point, then the first derivative test gives you a max or a min, and it's kind of like a global max or a global min. So another way of doing this is to say, well, let's look at the number line here. And these are my R values. So, well, first of all, I shouldn't even be able to start at 0, right? Technically, R has to be non-zero. If R was 0, you couldn't get 100 cubic centimeters of volume. So really, we should cut this off and say we're going to start at slightly bigger than 0. And then my one critical value here is going to be the cube root of 50 over pi. Okay, let's pick a number smaller than the cube root of 50 over pi. That's bigger than 0. Anyone have a good suggestion? I do. 1. 1's bigger than 0, and it's for sure smaller. Pick the obvious choice. You don't have to pick the closest thing. Like, I don't have to, like 50 over pi. Okay, 50 divided by 3 is like 16-ish. The square root of 16. Sorry, the cube root of 16 would be less than 2, not bigger than 2. But we don't write 1. 1's a safe choice. I'm sure it's going to be smaller. So pick 1, and you plug in r equal to 1 back into your first derivative. This is why you don't want to do what I did over here. We have to plug it in here. That's going to be 4 times pi times 1 minus 200 times 1. That's for sure going to be negative. 4 pi is like 12-ish. Minus 200 is for sure a negative number. Pick a number bigger than the cube root of 50 over pi. Cool, 1,000. 4 times pi times 1,000 is 4,000 pi. Minus 200 divided by 1,000 squared. That's a very tiny number there. So for sure, it's a big number minus a tiny number. That's for sure positive. Now, if your radius was 1,000, you'd have a very funny looking cylinder. It'd be like a pancake. Flat, wide, holds 100 cubic centimeters of volume, but it's very silly looking. So definitely here we do have a minimum. Great. Or you could have taken the second derivative and said that SA double prime is equal to 4 pi. Derivative is going to be plus 400 r to the negative third, which is equal to 4 pi plus 400 over r cubed. And if you plug this in, you exactly get, it's actually kind of more convenient than I thought it was going to be honest. You're going to get 4 pi plus 400 over the cube root of something cubed is just going to be the something. So you've got 400 over 50 over pi. And clearly that's positive. Right? I didn't even really need to plug it in to check. That's positive, we're good to go. Which means you would be concave up, which means we'd have a minimum at your critical point. So either way you want to do it, but typically typically they often do ask you to show that you actually have gotten the thing that you were supposed to have gotten. Because it is important to actually check. It is possible that you're trying to do, like, I remember the story my teacher told me when I was taking calculus was that someone in the Air Force was trying to build an airplane and they wanted to maximize the wingspan area, and they took the derivative and set it equal to 0 and didn't check their critical point, and they built a plane with tiny, tiny wings. I don't think it's true, but the point was you need to check because otherwise something bad can happen. So here we definitely have a minimum. We still have to finish the problem because the problem said, what are the dimensions of the cylindrical can that has this volume and minimum surface area? So we found the radius. We still need to find the height. So we go back, we look at the place where we wrote the height equation, which is 100 over pi r squared, and we plug r in there. So the height is going to be 100 divided by pi times the cube root of 50 over pi squared. And I think it's fine to leave it like this. I do want to simplify it for you just so I can make one observation. I know it looks gross. So let me rewrite this a little bit. So this is going to be, I'm going to write 100 as 2 times 50. Yeah. Okay, just hold on. So yeah. Then we have 50 over pi to the 2/3 power. What I really have here is 2 times 50 over pi times 50 over pi to the negative 2/3, which is really 2 times 50 over pi to the 1/3 power, or 2 times the cube root of 50 over pi. The reason I wanted to point this out to you is because this often happens. When you're trying to minimize surface area or maximize volume of a cylindrical can, you almost always get the case that the height is twice the radius. Or in other words, the height is equal to the diameter. So it's kind of funny to me, but the cans you see in the store, like especially the ones that have like the bigger cans of beans that have essentially the same height as diameter, they're really minimizing the amount of materials they have to use to build that can to hold the appropriate amount of beans. I feel like you see it mostly like for the Rosarito refried beans, like those cans are very much like they look like squares, except they're cylinders. So it's not just math for the sake of math, right? There are actual real world applications that we use this into help build things that cost the least amount of money or that get the most stretch for your materials being used. Cool. What time is it? 2:23. These problems take a while. Do we have time for another one? Sure, we have time for one more. Do we really? Maybe not. We definitely want if I keep just waffling and saying, let me look at this one. Let me look at this one. Sure, let's look at one more. So here's kind of a classic problem. It's not too terrible. We want to, I'm going to phrase this one slightly differently. We want to find the area of the largest rectangle that can be inscribed in a circle, in a semicircle of radius 5. Let's draw a picture. So typically when I'm drawing shapes and inscribing or circumscribing things, I often like to center my shape on the origin. So I'm going to draw my semicircle with its center, or the center of the full, where the center of the full circle will be at the origin. So here's my semicircle. Radius is 5, meaning this point is 5, 0. This point's negative 5, 0. This point 0, 5. I don't necessarily need to know all that, but it's not terrible. And then I'm going to draw my inscribed rectangle. So maybe my rectangle looks like this. And I'm going to label the sides. Now, what I'm really going to think about is the fact that this rectangle, the corner of it touches the circle at some point. Let's call it X, Y. The height of this rectangle is y. The base of this rectangle is what? It's not quite x, because x is this length here. And apologies for the lack of symmetry in my picture. It is 2x. Because this is x, this is also a length of x, so it's x plus x, which is 2x. So the area of my rectangle, the area that I'm trying to maximize, is 2 times x times y. Great. What's my constraint? What is my constraint? My constraint is that that point is on the circle. So you could either say, I know the equation of the circle and plug in x and plug in y for x. But the easier way here, and this is often true, is you want to kind of draw the segment that connects the center to the point of touching. How long is that segment I just drew? That segment that's the radius of the circle. It's got to be 5. Right? It goes from the center. If a segment goes from the center of the circle to a point on the circle, that's a radius. Every point on the circle or semicircle is the same distance from the center, which is 5 in this problem. So we know that we can say that Pythagorean theorem, x squared plus y squared equals 25, or 5 squared. So y is equal to the square root of 25 minus x squared. Not plus or minus, just the positive square root, because I only have the top half where y is positive. So then I'm going to substitute that back in here to be able to write my thing I want to maximize as a function of one variable. So area is equal to 2 times x times the square root of 25 minus x squared. Or more nicely written so that we can differentiate it, 2x times 25 minus x squared to the 1/2 power. Great. Let's take the derivative. A prime of x is going to equal 2 times 25 minus x squared to the 1/2 plus 2x times 1/2 times 25 minus x squared to the negative 1/2 times negative 2x. Gross. Here is where our factoring skills need to really be strong. So I need to simplify this, and I see that I can factor out the 2 from each of these. So I'm trying to set this equal to 0. I can also factor out the 25 minus x squared to the negative 1/2. Here, I'm left with a 25 minus x squared to the positive 1. You can either say 1/2 minus negative 1/2 leaves me with 1, but I think it's easier to think about if you multiply this back through, you would add those powers, and negative 1/2 plus 1 is positive 1/2. So it works out. From over here, I'm factoring out the 25 minus x squared to the negative 1/2 and the 2. So I'm left with x times 1/2 times negative 2x. The 2's cancel, and I'm left with a minus x squared. Rewriting this, I'm going to write it as 2 times 25 minus x squared is 25 minus 2x squared over 25 minus x squared to the 1/2, or the square root of 25 minus x squared. Kind of terrible. So what are the two values of x that make this expression undefined? Well, if x was 5 or negative 5, you would have division by 0. But I think you can see that if x was equal to 5, your rectangle would be flat, right? There'd be no area. So clearly x equal to 5 is not the thing we're looking for. The other critical value is by setting the numerator equal to 0 here, and that's going to give us, I know it's 230, so I'll wrap this up. 25 minus 2x squared equal to 0. You're going to get 25 equal to 2x squared. X squared is equal to 25 over 2. So x is equal to plus or minus the square root of 25 over 2, which is really plus or minus 5 over root 2, which is plus or minus 5 root 2 over 2. that does give us a maximum. To find it, no, we don't have time. I'll just say it does, and we talk about it next time. And then to answer the question, here they didn't ask for the dimensions. They asked for the maximum area. So you would take this value here and you plug it back into your area equation. So the maximum area would be 2 times x, which is, I'm going to write it, no, yeah, it's 5 root 2 over 2 times the square root of 25 minus, let's write it as 5 over root 2 squared, which ends up being kind of nice. The 2's cancel here. You get 5 root 2 times the square root of 25 minus 25 over 2, which is really 5 root 2 times the square root of 25 minus half of 25 is half of 25. And that's going to be 5 root 2 times 5 over root 2, which is 25.